Welcome to the demonstration of LaTeXSolver, which is our application for operations research experts to convert an input LaTeX document describing an optimization problem or decision-making problem into an optimization model, which can be instantiated or loaded with data, passed to a commercial solver to obtain the optimal solution. For a little bit of background, here is a simple problem described in LaTeX. This is an alloy producing problem. We're trying to produce a lead, zinc, tin alloy and minimize cost. There are some defined sets, alloys and elements. Specifically, you have parameters which depend on those sets. We also have a decision variable, and the objective is to produce this alloy and minimize the cost. So we want to minimize this expression. To highlight a feature, I've replaced the correct parameter, which should be unit cost, with required ratio. And there are also some constraints listed here. Now on to the application. You can click to create a new model. Here are some categories that you can select. And this helps you when you share your model with other experts. Other experts are able to filter for the domain that they're interested in or that they're working on. And also with these tags, they can look for keywords. And potentially find your model for inspiration, or you can have conversations through that. Let's call this alloy creation. Select the type of input type, which is LaTeX, and we will upload that alloy text file. And also describe, minimize cost while creating. And after you click confirm, it'll be added to the list of your created models. Minimize cost while creating alloy. You can pin the one you've just created, minimize cost, and you can select that. Here, there's a top panel, which allows you to create new sets, parameters, or these components by clicking it, these cards. And also this is the card view of the model. We have our sets, parameters, and variables, and our objective and constraints. These are the components that were extracted from the LaTeX file. The sets have fields, name, and description, and you can revise these. And variables add on a category or type. This can be one of continuous, integer, or binary. You also have a lower bound and upper bound, and you can relate it to alloy or element. We also have our parameters, which is has the name, sets, and description. These gray lines represent which sets are tied to which parameters. So V uses or depends on set alloy. And as you can see here, ratio, it depends on both sets, both alloy and element. Similarly, for objectives and constraints, these gray lines signify which parameters or variables are used in the expressions for these objectives and constraints. As I've described earlier, I replaced unit cost with required ratio. So you can simply just replace this here. You can also change the sense to maximize and minimize. You can recreate the expression by building it like so. And here we can also update the description. And let's say we want to describe this a bit better and say this is an upper bound. This is a lower bound, non-negative constraint. And we can save all of those changes. Save our changes. Get to unit cost. And now let's say as an OR expert, I'm satisfied with these expressions. I can create a data card, which allows us to upload our data, alloy data, and you can also select which objectives and constraints to use. Let's say in your model, you want to explore different objectives or a variation of the same constraint, but slightly different values for the parameters or slightly different parameters. You can simply explore these variations by selecting or deselecting some, and this makes comparing different models very straightforward. After you save, you can see which ones are used, and as we click solve, you can also select which commercial solver to use, and for now we'll use the Huawei Opera solver. And while that is solving, we can take a look at what the data, how the data is represented. For our, I will scroll a bit. For our sets and parameters, we have the sheet names here corresponding exactly to the name used for the parameters and sets. Sets will list their available values. So there are two sets here, alloy and element. For one-dimensional parameters, you'll list out that set and the corresponding values. For two-dimensional, you will do you'll list the two sets and the corresponding value, and so on for higher dimensions. Now this is the objective value, and you have this optimal solution. Let's say now you want to change the values of the unit cost. Say the day has changed and you have new rates for these alloys, just entering random numbers. You can save this as a version 2. And when we create a new data card, we can use alloy data version 2 and say, before we click solve, we can always version control and specify this as version 1.1 and say this is a new day's updated unit costs. This makes it very straightforward to keep track of which data file was used, and you can also take notes and compare your solutions. Objective value is different. However, the variable value remains the same for the optimal solution. Now I would like to show a more difficult problem. This is the scooter, where floating e-scooters can be picked up from locations and dropped off. And it's more difficult because there are more parameters and I believe 7 constraints to consider. So we will create this in the same manner. For the sake of time, we will just speed through this part. Scooter location, we'll select LaTeX, and our scooter LaTeX file. We'll skip the tags and also the description for now. After that is done, you can click into the scooter location, and you can see that there are 7 constraints. It's a more difficult problem with more complex expressions. We can also give this expression or this constraint a name. We can say it is an upper bound. Sake of time. We can add our data card, point to the scooter data, save, and click solve. Once again, we'll choose the Opera solver. And please note that there are 3 decision variables here for this problem to consider. And when looking at this solution, you can see the optimal solution for all 3 of these variable values. thank you for your time and your interest. We look forward to seeing you in person at ACL. There was too much information to fit into a short demonstration, but we look forward to connecting with you. Thank you.